Ladies and gentlemen, welcome to the third section of this lecture. Please calm down a bit. Now there are a few questions which have been given to me in the break, and I would like to address each one of them now in the row like they are here. Now the first question: how does the immune response in bone work if there is so little blood supply? This is, of course, a very intelligent question, because we all know that for the immune response, typically we need blood. We all know that if we hurt ourselves, if we have an injury, we get the typical response, rubor, dolor, color, and so on. So there will be a lot of blood supply available, and out of this, the immune response will be supplied, and in the end there will be a healing and the infection will be fought. Now in bone, the situation is a little bit different, because in bone simply can't turn up the blood supply so easily, because there are no blood vessels, and of course in the Haversian canals we cannot increase the blood supply. So how does bone defend itself? Well, bone, very simply, in very simple words, defends itself by the high mineral content. So the very high mineral content, this calcium phosphate, is so high that simply the bacteria cannot live inside. And there are only a very few, actually only one real exception to this, and this is the osteomyelitic infection. In the case of the osteomyelitis, the infection is inside the Haversian canal. So really the infection is in the bone. The bone is actually infected. So typically bone works without a lot of blood supply, and bone can defend itself without blood supply against infections. The next question is regarding biologic osseointegration. I have mentioned the term biologic osseointegration. Are there other ways of integration also? Well, to answer this, please think about the implants, about fracture plates and screws and traumatology. These implants are integrated immediately. So as soon as the screw of the fracture plate is in contact with the cortical bone, there is no other reaction necessary. It simply is integrated, and there is no such thing as a biologic osseointegration to those parts of the implants which are in contact with the cortical bone. So a kind of immediate osseointegration is possible. Osseointegration, and let me remind you of this, osseointegration means only that there's a direct contact between the implant and the bone. It doesn't mean, or it doesn't presuppose, that the bone actively does anything to accept the implant or to actively integrate or like to hug the bone. This is not necessary. It's the term osseointegration describes only the result, the direct contact between the implant and the bone. So the immediate osseointegration of the cortical bone, the direct contact between the cortical bone and the implant, also is osseointegration. The next question: if the implant surface is not incentive for the bone to grow onto, why then does bone heal? Well, in short, if there is no implant inside the bone will also heal. And simply the bone heals because the corticals want to close, and well, as long as the implant is not preventing this, the bone will do exactly this. So as long as the implant is not toxic or preventing anything, or as long as into this hole, let's say, or in this fracture area between the two parts of the bone, for example, no vessels are growing into, then this gap will be closed again with bone. And typically there is bone inside the bone, so it's not necessary to have an implant inside the bone to have the bone healing. The next question is a very practical question, because we see basal implants made from plastic appearing on the market, the PEEK implants. So what is your opinion about PEEK basal implants, or PEEK as a bone implant material? Well, in general, we know from traumatology, from orthopedic surgery, that basically PEEK is a good material for replacement of bone. So we see a lot of limbs, intervertebrate discs, and so on being produced by PEEK. This works well, and in those fields there is no problem with this material. We have to accept, however, that the bone-to-implant contact between PEEK and bone compared to titanium or titanium alloy and bone is much lower. So if the bone has to grow onto PEEK or onto titanium, you will see much better growth on titanium or titanium alloy compared to PEEK. So it looks like PEEK can work in many fields. It can work in traumatology and it can work in other reconstructive fields, surgical reconstructive fields of bone, but probably it doesn't work so well in the dental field. This is one of the reasons. I have seen a number of cases where PEEK implants were buried deep inside the bone, so the place of the potential infection was far away from the base plate, and in those cases the implants worked well. However, this is not the main indication of basal implants. You know, basal implants, especially lateral basal implants, are used in low bone situations when you have 3, 4, 5 millimeters of bone and you still want to anchor an implant. And in these cases, according to my experience, PEEK doesn't work well because it's not protected against infection and because probably the affinity of the bone growing onto the implant is too low. And there is another problem of PEEK, and I want to show you this on the slide. So this is a picture of implants which we have taken out. And as you can see, the main idea of these implants is that the surgeon can cut intraoperatively the base plate of the implants according to the shape of the bone, but what is left then are sharp edges, and these sharp edges, for example, as you can see them here, down here, or down there, or over there, these sharp edges then will lead to an overload osteolysis, so the bone will receive too high loads in exactly these areas, and then the integration of the implant will fail. So this is one of the reasons why I do not recommend to use these implants. The other problem, of course, is that the splinters, the things which are just cut off from these implants, can remain attached to the implant. So this will lead to an irritation of the bone or the soft tissue. And the next point, of course, is that these holes, which are designed for perfusion of the bone, are too small. We know this from the old disc implants which were produced by Scotecci in the 70s and 80s, that it is absolutely necessary to have these holes big enough. And from what I have seen on the market, there are no PEEK implants on the market available with holes which are large enough to allow perfusion. The main idea of PEEK implants, of course, is the isoelasticity. So the manufacturer claims that because this implant is isoelastic to the bone, the integration will be perfect. Now, if you remember the part 1 or 2 of the lecture, I don't know exactly, I have shown you one slide about the properties of bone, different bones. I show you this again. This is the mineral content of elk antlers, cow femur, and whale bulla. This picture shows you clearly that there is no such thing as a typical mineral content. You see here that the elk antler has 59 weight percent mineral content, the cow femur 66 weight percent, and the whale bulla 86 weight percent. So this all is cortical bone. And of course the elastic properties of those three bones are different. The fracture resistance is different, the flexural strength is different, and this is so this means that bone can adapt to the situation where it's used. It will adapt to the demand, and it is not true that that bone and jawbone especially has one typical mineralization or one typical elasticity modulus. In fact, this changes throughout life. This changes, the elasticity changes according to the demand. So there is no need to use a material which is isoelastic to one of these situations, and we can work well with titanium. We know this for at least 50 years that this works. Now the next question refers to to the integration of implants. Are there any disadvantages to polished implant surfaces? Do they integrate? As I pointed out before, of course, titanium as such integrates very nicely. Titanium is passivated, so there's an oxygen layer on the titanium, and this leads to high biocompatibility. I want to remind you that these old Russian submarines of titanium class, they were the outside of these submarines were completely made out of titanium, and that's why all these algae and all the stuff in the sea was constantly trying to integrate. So they had to polish these implants like these submarines like mad. And it's actually the same with the titanium implants. Titanium simply is very compatible, and living cells and living creatures tend to live well on it. And of course, polished implants just integrates as anything else. Of course, all traumatology implants, all the implants used in orthopedic surgery are polished. Okay, there's no such thing as an aselective surface on implants in traumatology. Now, the last question, how is it possible that so thin implants can carry so much load? Well, I've shown you before in part one of the lecture that most of the implant anyway is not integrated, only the part projecting towards the cortical is integrated. So this means, on the other hand, that of course also implants with thin implants and implants with a low surface can carry a lot of load as long as they are integrated. So we don't need a big surface, we don't need surface enlarging, we don't need sandblasting, and we don't need acid etching. Anyway, in the reality, this acid etching is only done in order to wash off the remnants of the sandblasting material, for example, aluminum oxide. So the acid etching is not really designed to clean it's designed to clean the implants and not to increase the surface. So these are the questions which I was given in the break. I hope that all your questions are now answered. Thank you very much for the attention. Goodbye.